Okay, young learner, let's do one more question, numerical problem, related to the emission lines that we get um, for hydrogen atom. The question is taken from the NCERT textbook of class 11 chemistry, lesson number 2, the chapter number 2, the structure of atom. Question number 2.15. What is the maximum number of emission lines when the excited electron of a hydrogen atom in n equal to 6 from 6 orbit drops to the ground state? What are the maximum number of emission lines? Well, what is emission lines? So we know that when any atom in its gaseous state, we make sure that electromagnetic radiation is passed through it, or it's heated. Um, it absorbs the electromagnetic radiation, or after some time it may again emit electromagnetic radiation. So when it is led to pass through some kind of prism, we can see the spectra, which may be visible to our eyes if the wavelength is within the visible range, or it may not be visible to us. So for hydrogen atom also, when hydrogen is in its gaseous state and we uh, pass through electromagnetic radiation through it, what will be seen in the plate is the spectrum or spectra of hydrogen atom, which is very unique to hydrogen atom, and it will have some absorption spectrum or emission spectrum. So it's an absorption spectrum, just like the negative of our photograph. So and those so it is why the spectrum is related to the structure of the atom, how electrons are arranged in it. So a spectrum of an element is very unique to the atoms of that element, how the electrons are distributed, how much energy they are possessing. But in the very earlier times, Johannes Rydberg, uh, the Swedish physicist, he calculated, he have given a general relationship which is used to calculate the wave number depending upon, for hydrogen atom, depending upon from which orbit the electron is jumping from. That is jumping from, initially it was in n1, then the final orbit is the nf. Yes, the relationship is given by 1096771 by ni square minus 1 by nf square. This is the initial orbit and this is the final orbit, and it's given that the final orbit will be more is more than the initial orbit. But that means this is more than this, means this value is more than this, then it will have a positive value. This is nothing but the relationship equation which gives the wave number. In our case, the question is saying, what are the maximum numbers of emission lines that can be seen when an electron draws from the sixth orbit and it comes back to the first base. See, this is the hydrogen atom. I'm just making a rough diagram of it. It's a proton over here, and the electron may be in the first orbit, in the second or third, fourth, fifth, or sixth. The electron is going to drop from the sixth orbit, to any of the orbits. See, the beauty of this question is the electron may drop to any orbit. It may be from 6 to 5 or 6 to 4 or 6 to 3 or 6 to 2 and 6 to 1. And remember that when an electron is in any energy state, this is in what the Bohr calls that stationary states, while in which the electron while revolving doesn't emit any energy. Yes, but when electron jumps from one orbit to another, from higher to lower or from lower to higher, it may emit, or it may absorb, or it may emit electromagnetic radiations. But it will be very unique, because the energy in this E1, E2, E3, E4, E5 is very unique. So difference of energy from E1 to E2, or from E1 to E3, or from E1 to E4 will be very unique. Unique in the sense that energy will come out as photons, right? And photons, the amount of energy in each photon is given by E equal to h into nu, which is the frequency, and that frequency again linked to the wavelength by this equation, in which the product of the wavelength and the product of the wavelength and the frequency of any electromagnetic radiation is same. It will be the velocity of that electromagnetic wave that is 3 into 10 to the power 8 meter per second, that we generally know is the speed of light in a vacuum. Okay, so once we get the frequency, the energy is fixed. That means the energy that will come out will be fixed. There's some allowed energy. So it's the corresponding frequency will be unique, and the corresponding wavelength will also be unique, and thus the corresponding emission lines and the spectra will be unique. So in other words, we can take this question as saying that what are the energies, different kind of energies, different amount of energies that will be released when an electron jumps from 6 to any of the orbits below it. So how many jumps, how many kinds of jumps he can make? It's like asking like that, because every kind of jump will be associated with it with a unique amount of energy, which will again in turn will have unique frequency, and that will in turn have a unique wavelength, right? And that will have a unique lines, the spectral lines in the photographic film. Okay, so let's find out how many special jumps he can make from 6 to 5, 6 to 4. So suppose he's jumping from 6. The question says from jumping from 6, so 6 to 5, 6 to 4, 6 to 3, 6 to 2, 6 to 1. So there are 5 kinds of jumps. So this is 5. That means there will be 5 kind of energy related. The 5 amount of the difference energy will be E6 minus. Suppose if it jumps from E6 to E1, it will be E6 minus E1. If it jumps from E6 to E2, it will be E6 minus E2. If it jumps from E6 to E3, it will be E6 minus E3. Just like that, right? So amount of energy in this will be more than this, will be more than this. This is more than this. This is more than this. This is more than this. So it will, as you go on, its amount of energy it will have more energy. At infinity, the amount of energy is 0, which is the maximum energy. When the electron has no influence of the nucleus. That's an assumption that we have. That is a postulate that the Bohr is mad, right? So for example, so if it jumps from 6 to the inner orbit, there are 5 possible jumps, right? If it jumps from 5, it'll be first 5 to 4, 5 to 3, 5 to 2, 5 to 1. So there are 4 possible jumps. If it jumps from 4, 3 to 1. So there are 3 possible jumps. If it jumps from 3, there are 2 possible E2 or to E1. 2 possible. If it jumps from E2, there's only 1 possible jump, E2 to E1, right? So these are the possible jumps from or shift of electron from the different orbits. So total, how many shifts are possible? 15 shifts are possible. 15 emission lines are possible. That is what the question is asking. I hope it's you have understood the things. Now the radius. What about the radius? The radius of the orbit, as calculated by Bohr in his theory, is radius at any nth orbit is given by n square into a naught, where n is the principal quantum number, first orbit, or like it may be first maybe 1 or 2 or 3 or 4 or 5, 6, not in between, to the whole number, right? The first orbit, if it is a second orbit, 2 square. If it is third orbit, 3 square. If it is sixth orbit, 6 square. 6 square of what? A naught. And what is A naught? It is fixed value 52.9 picometer, and it's also called the Bohr orbit. What that means is if we can find out the radius of the first orbit. For that, you have to put the value of n as 1. So 1 square is 1. That means the radius will be A naught. A naught means 52.9 picometer. So in a hydrogen atom, the radius of the first orbit is 52.9 picometer. Pico is 10 to the power minus 12. So the electron will be 52.9 picometer away from the nucleus. That's what we call the Bohr orbit. And what will the radius when it is in the 6th orbit? Multiplied by 6 square. We put the value of n as 6 with 36 times of 52.9 picometer. Fine.